So what are the main types of radioactive decay? So this is section 10.4. So what we're going to do is we're going to go through all of the main types. So the first type is going to be alpha decay, alpha. Remember, an alpha particle is a helium nucleus. So what happens when we're doing the equations, nucleus, we have to, like chemistry equations, we're going to do a radiation breakdown equation. We're going to use this one. We have to have the same number of protons and neutrons on both sides of the equation. Let's take an example. Say we've got uranium 235, U235. So it's 235 nucleons in the middle, and there's 92 of which are protons. And if we wanted to, I assume we could work out 143 neutrons. Now this is the unstable form. It's metastable. It lasts quite a while, but it's still. There's two types of uranium, 238, 235. This comprises 0.7% of the naturally occurring uranium because it breaks down faster than the other one. Okay, but say we have uranium atom and it breaks down. So it spontaneously breaks down. And what are we going to end up with? Thorium? What's the 2 under thorium? Protactinium, thorium. What's going to happen? Plus an alpha particle. Now what we know is in the alpha particle, because it's a helium nucleus, remember, it's got 2 positive, 2 negative. It's a helium nucleus. So we know the alpha particle is going to have 4 nucleons, and it's going to have 2 protons. So if I look at this one, if I'm trying to work out what this is going to be, I look at this and I go, well, there's 92 here. If I take away 2, that means there's 90 left. And if I look at this one, there's 200. I start off with 235. I take away 4. That means I've got 231. And that's going to be a fairly unstable form of thorium, and that's going to break down itself to protactinium, and away you go. But anyway, what we have to do whenever we're doing these equations, the number of protons on this side must equal the number of protons total on this side. The number of nucleons on this side must equal the number of nucleons on that side. As a general rule, this is going to be there's one where so basically the number of nucleons has to be conserved, but we have to account for all of the protons and things. So let's try another one. Let's take example 10.1. So this is a classic alpha particle emitter. We're going to use radium 226. It's quite radioactive. It was quite funny when the Curies were doing their research. They basically had a ton of uranium ore. They extracted the uranium, and the crap that was left over was more radioactive than the uranium. And they found out there was like a fraction of a grain of radium in there. So this is going to, radium 226 is going to emit, it's going to break down, and what we're going to end up is we're going to end up with a alpha particle. And we know alpha particles have 2 protons and 4 nucleons. So if we go 88 minus 2, so this, whatever this mystery element is, it's going to be 86. And we go 226 minus 4, so 222. So if I go 222 plus 4, that's 226. If I go 86 plus 8, that's 88. And this is going to be radon. And radon is actually one of the big nasties in many ways because it's actually a radioactive gas. And this is actually responsible, strangely enough, radon is responsible for most of the, well, huge amount of background radiation and where most of the helium comes from in the world. So if you blew up a helium balloon, it actually came from radon. Okay, so that's a classic one. We also have the next type of radiation that we have is beta minus. Now, beta minus is an electron. And the reason, and remember, if we have a nucleus, what we have is we've got plus and new. We have a electron gets spat out of that center. But we've already seen from the section where we're doing de Broglie waves and like quantum stuff, electrons cannot exist in the center of a nucleus. So where does the electron come from? And the answer is very simple. A neutron is a proton plus an electron. So what happens in this case is that a neutron will fall in half, and that will turn into a positive. So that'll turn into, the neutron will turn into a plus. And there's also, the neutron also has an electron, but the electron can't actually physically exist in the nucleus, so it gets spat out. So beta minus, we also write it as beta minus, is your standard beta decay. When we talk beta decay, unless we mention otherwise, basically it's beta minus decay. So when we're talking about a product, or so if we're talking about something, if we have our thing, our mystery element, and let's just make up a mystery element 26, 10, for example. This is not a real element, it's just being made up. But if it does a beta decay, you'll notice that the neutron changes into a proton. Proton is still a nucleon. So the number of nucleons does not change. But because it turned from neutron to proton, now we have one more proton. So now it's actually, because the number of protons is now different, it's actually a different element. So we're going to get that, plus we're going to get our beta. So we're basically going to get our electron. And we're also going to get a neutrino coming out of here. We probably don't have to write this, plus there's a neutrino. And this is basically a small massless particle, which is incredibly fast, got lots of energy, and it's a bit like a photon, but it's actually solid. Okay. So this is your standard beta minus. This electron, yeah, if it hits the wrong part of your body, it can cause cells to die and chromosome damage and things. So I don't really recommend handling large beta emitters. But I've got radioactive glass around here that's alpha emitters. Okay. Anyway, that's beside. So let's take example 10.2. Let's actually apply this with a substance. So what we're going to have is we're going to have beta decay of carbon 16. God, that's got to be an unstable atom. So we've got carbon 16. So because it's carbon, it's got 6 protons. And we know that this is going to emit a beta particle. So we end up with something plus an electron. Pump. Okay, so what we know, if this is a beta decay, we know that the number of nucleons does not change. So we're still going to have 16 nucleons, because remember, one of the neutrons turned into a proton and electron, spit the electron out. But the number of protons has increased to 7. That means it's no longer carbon, doesn't act chemically like carbon anymore. This is now nitrogen. Okay, so this is cool that we actually do use this stuff occasionally, even occasionally for electrical generation. It was used in things like the gold tinfoil experiment, beta emitter. We've used all sorts of things, beta emitters for all sorts of things over the years. So we do actually use this stuff. This isn't just theoretical. Remember, they have a beta emitter in the Huntley Power Station, or they used to. Basically, they shot the electron beam across and used to check to see the coal was falling through. Good. Okay, so there's another type of beta decay that we can get. This is much, much rarer, but it's still, we actually still commonly use this in industry, this beta plus decay. And what actually happens here, remember what we said, beta minus equals an electron. Beta positive is equal to an electron with a positive charge. This is called a positron. And this is actually a form of antimatter. So antimatter, a positron, is going to be an electron, have the same mass as an electron. It'll orbit around its electron, but it's going to have a positive charge instead of a negative charge. And if that ever meets a basically, if that ever meets a electron, well, yeah, there's going to be a bit of an annihilation, lots of energy coming out. But how does this actually turn this? But basically what happens is, in this case, this is called by proton decay, believe it or not. So a proton, so basically we start off with a proton, and it spits out this positive charge. And that means what's left has got no charge, and that's going to be a neutron. And there's also going to be our neutrino, which carries a lot of energy here. And we actually use this in medicine. This is, we have what we call PET scans, positron emission tomography, which basically uses a chemical which has got a beta plus emitter in it. You drink that, and then they pick up all the annihilations and antimatter explosions in your body. Really cool. Okay. So, so what happens here when we have our mystery element? Let's say we have a mystery element 10, and let's say 5. It's going to, remember, when we're doing these equations, the number of nucleons does not change. So what we're going to end up with is we're going to end up with an E plus our neutrino. But, so the number of nucleons doesn't change. But what's going to happen is a positron is going to turn into a neutron. So if we look at my nucleus, this turns into a neutron. That means we have one more neutron, that's fine, but one less proton. So the number of protons decreases. And what's 4? 4 is beryllium. So that would be boron decays into beryllium. So again, this is just a made up number. Okay, so this isn't a real reaction. This bit's sort of real, but this is an example. We'll do an actual one with real element and see. But you'll notice here, the number of nucleons does not change. But yeah, in this case, the proton does change because, yeah, we turned it into a neutron. But so this has got 5 protons, 5 neutrons. This has got 4 protons, 6 neutrons. So still the same. So what does actually do this? Well, in the hospital, they use oxygen 18. That's quite standard of positron emissions. But we also get this with carbon 11. Carbon 11, if that's going to do a beta plus emission, we're going to end up with a positive electron. The number of nucleons does not change, but the number of protons decreases. Because the number of protons changes, it's now a different element. And the element with 5 protons is boron. Now that's cool. Okay, so we're going to deal with that. So this is rarer than beta, but it still happens. We're going to do an even rarer one now, which is electron capture. So I'm just going to capture this one. So electron capture is basically happens the opposite way. Oh, not common, but so basically we have an electron, it goes in, and it joins, so basically an electron comes in from outside, gets captures a proton, and we end up with a neutron. Usually it will go the other way, but this does happen. So basically, if we have our element, let's just make up an element 2010. I'm not saying this is a real process. Plus, well, and then we add an electron. So this is one of the few times when you actually have a plus on this side. Well, what we're going to have here is we're going to still have the same number of nucleons, 20, but what happens is we turn one of these protons into a neutron. So the number of protons are going to decrease. Yay. Okay, so yep. And yep, so let's actually try this again with the real thing. So what we're going to do, we have beryllium. So beryllium 7. Beryllium 7. So this is, what's this exercise? 10.4. Plus a electron. Feel free to pause it at this point if you want to do it yourself. So what do we end up with? We end up with number of nucleons stays the same. But now this changes down. We lose one of the protons, it turns into a neutron. So this becomes 3 and it's going to be lithium. So it's going to turn into lithium 3. And the last one of our main zoo of radioactive decays we're going to deal with is we're going to deal with gamma radiation. And remember, the big three usually we wrote about are alpha, beta, gamma. So the electronic capture happens, beta positive happens, but the big three are alpha, beta, gamma. The others are much rarer. Okay, so anyway, let's carry on. Let's just do gamma radiation. And remember, the thing about gamma radiation is a wave. It's a photon. So it doesn't actually change any number of protons or electrons. But remember what we had, when we have our atom and we have our shells, electrons will try and drop down a level and will try and get to the lowest energy state. So if you have an electron up here, it'll drop down here, and an electron up here, drop down here, and it will emit a photon. Poof. Same thing happens, or a similar thing happens inside the nucleus. Sometimes these do not pack nice totally, and you end up with a gap. And occasionally one of these will fall into the gap because the gap is now a lower energy level, and everything will squish down on it. It's a bit like taking out the bottom brick of a very, very tall tower. Everything's going squish on it. And because everything's going squish, it's like a bump in the mine. Bump in the mine is when you draw a drive or have to passage along, and every now and then the working will go squish. And because it's got huge amounts of weight above it from the dirt, a lot more energy than if you just drop a rock on the surface. So these, because of this extra energy, it's going to have a huge amount of energy, and it's going to emit that as a wave. Very similar process to the electron energy states we were talking about. Okay, so if we have our mystery atom, I don't know, 60, 30, and it spits out a gamma ray, well, the number of nucleons isn't going to change because a gamma ray doesn't have any protons, it doesn't have any neutrons. The number of protons doesn't change, so we're going to end up with what we started with. And in fact, let's use something like cobalt-60. Cobalt-60 is a highly radioactive source. It's often used in, or used to be used a lot in cancer machines because it's a fairly simple source. So cobalt-60 is quite highly radioactive. It does a gamma ray, gamma emission, and that's what they used to use in the radiation therapy, because gamma rays will penetrate the body so you can get in and kill the cancer. Well, it emits a gamma ray. Well, how many protons? Once it's emitted the gamma ray, how many protons has it got? Well, 27. How many neutrons has it got? Well, 27, because it hasn't shifted. All it's done is rearranged the nucleons. It hasn't got rid of any. So because it's still got 27 protons, this is still cobalt. Okay, so those are the basic types of things. So shortly we'll do radioactive clocks and half-lives and things, but good luck.